Hello, everybody. Welcome back. Today we're going to take a look at more Fourier series and actually apply it to real-life sound waves. Okay, so this question asks us to find the harmonics and the relative intensities for the following sound wave. And our sound wave is given here in this function here. But that's a little unwieldy to read, so I went ahead and drew it out right here. Okay, so this is so x is in seconds, and from negative 1/220th of a second to negative 1/330th of a second, it's at -1. On this next interval, it's 0, and then on this interval, it's 1, 0, and then -1 again. And then it keeps on repeating. So the next part would be it continues on like that, and then goes up here. You know, it's a periodic function. So one thing you might notice right away is that this function, you can reflect it along this axis here, and it coincides with itself if you do that. So we call that an even function. Now, even functions have some special rules that help us out with some things. Mainly, we'll be using these ones here. Remember, this here is our equation for our normal Fourier series. But if we know that f of x is an even function, then we know that all of the b of n's are 0, and we can find the a of n's using this formula instead. So we'll go ahead and do that. Yeah, we'll start with the Fourier series. We're going to need this sine function a lot in the latter half of this problem, so I drew it ahead of time. Okay, so the average value of our function is 0 because it spends as much time above, this part cancels out with that part cancels out with that part. So our a of 0, whoops, oh, that's fine. Our a of 0 is equal to 0. Um, and then for the rest of our a sub n's, we'll use the formula here because we know that f of x is even. Well, f of x is an even function. So these L's that are popping up, these are 1/2 of the period. So in our case, L is equal to 1/220th because there's a full period every 110th of a second. So a half of a period is 1/220th of a second. Okay, f of x cosine of n pi x over L dx. Okay, so making some substitutions. Since so our L is 1/220th, so putting it on the bottom of the fraction brings it up to the top, so we have 440, 0 to 1/220th of our f of x, which we will take care of in just a second, cosine of 220 n pi x dx. So once again, since this is a piecewise function, our f of x is a piecewise function, we need to split up the integral over all of these things. But you can see that over this middle section, remember the sum is going from here to here. This middle section here is not going to, we're going to multiply by 0, so we can get rid of that part of it. So that leaves us with, and then this part here, we're going to be multiplying by a -1 as our f of x. So we're just going to subtract that instead of multiplying by a -1 because it's the same thing. So we have a of n equals, we'll bring this out front, where we will split up the integral. So from 0 to 1/660th is just going to be cosine of 220 n pi x dx. Then we're subtracting from 1/330th to 1/220th of cosine 220 n pi x dx. Closing parenthesis. Okay, so now we can take these integrals. It's not so bad after all. It's just sines and cosines, which we've certainly dealt with plenty before. Okay, so 440. So when we take the integral of these are going to pull out 1/220 n pi. So I'm just going to skip a step and just take it out in front. It's going to be the same for both of these integrals. So just save us some room and do it right away. The x doesn't tag along because we're integrating with respect to x. Yeah. So this turns into the integral of cosine is sine. So sine, since we took care of the inside, we don't have to deal with it. 220 n pi x from 0 to 1/660th minus same sort of deal here, sine of 220 n pi x from 1/330th to 1/220th. Okay, so I'm gonna go ahead and substitute some of these things in, and we'll see where that takes us. So first of all, that obviously just ends up being 2 n pi out in front. And so when we plug this in, we're plugging this in for x. So we end up with sine of, yeah, so 220 over 660 is 1/3. Actually, it's 1/3, but it'll be overall n pi thirds. And we're subtracting this one, so we substitute in for x, which is 0, so that leaves us with 0 since sine of 0 is 0. And then we're subtracting sine 220 over 220 is 1. So we're going to have n pi, and then we're going to doubly subtract, or also known as add, sine of 2/3 n pi. And we still need a closing parenthesis. So yeah, so take a look at our graph here. I drew it here for a reason. And I also divided it up into thirds for a reason. Who would have guessed? So notice that when x is a multiple of pi, no matter what multiple of pi, sine of x is going to be 0. So we can take this out because it's going to 0. Now, for these next steps, for simplifying the rest of it, is a little bit more complicated than that. So, we're going to have 6 cases. So I'll label these. So we're gonna say that this is a of 6k. That is, n is a multiple of 6. So for this first one, all of these are going to be multiplied by this. I'm going to keep that in there. I could say 6k, but I don't feel like it. So when n is a multiple of 6, what do we have here? We have a multiple of 2 pi on here, and we have a multiple of 4 pi in here. Remember what we said about multiples of pi? For multiples of pi, sine is 0. So we have a 0 plus a 0 equals 0. And now, for the next step, what if n is a multiple of k plus 1? So, like your 1, your 7, etc., your 13. So we're still going to have this factor out in front, as usual. But let's see what we get on the inside this time. When n is a multiple of 6 plus 1, that means that sine of n pi over 3 is 3 pi over 2. Because whatever, it's always at the start of its period, and it's 1/3 past that. 1/3 past the start of its, where it starts over its period. So that leaves us with pi, or the square root of 3 over 2. And what about for 2/3 n pi? So at this same spot, that term is 2/3 past its original starting position of the period. So that means 1/3 goes to here and 2/3 goes to here. It's obviously going to be at a different period than the first function, but it is still going to be 2/3 pi past the start of a period. So that leaves us with square root of 3 over 2, which obviously those combine together to make a square root of 3. So this gives us 2 square root of 3 over n pi. Now for what if it is 2 plus a multiple of k? So when it's 2 plus a multiple of k, so our n pi over third term is going to be 2 past the beginning of a period. So it's going to be square root of 3 over 2, as expected. So I guess we can fill that in right now. Square root of 3 over 2 plus, and then this term is going to be 4 past the beginning of a period. So consider, we start over here. So this is 3 past the beginning of a period. This is 4 past the beginning of a period, going back, over here. So that is a negative square root of 3 over 2. Notice that these terms, these terms are non-zero, but they cancel each other out. So this brings us back to 0. Then for this next one, when it's 3 past a multiple of 6, we can actually use the same logic that we used for just a multiple of 6. Since nothing we did revolved around 2 pi, it all revolved around pi, but we'll just go through it again. At 3 past a multiple of 6, this is going to be pi, this is going to be 2 pi. Every pi, sine is 0. So that's going to be this term again. 0 plus 0 equals 0. And what if it's 4 past a multiple of 6? In that case, we still have this term out in front. And at 4 past the multiple of 6. So our first term, so this is 1/3 past, this is 2/3 past, this is 3/3 past, and this is 4/3 past. So this is going to be negative square root of 3 over 2. What about this term though? It's going to be 8 times past the beginning of a period. So 1, 2, 3, 4, 5, 6, 7, 8. So at 8, we got back to our positive, or you could just say at 8 past, it's also going to be 2 past the beginning of a period, since a period is 6 long. The way we're looking at it. So, yeah, when that's the case, this is going to be positive square root of 3 over 2. Notice that those still cancel each other out. And then finally, what if n is 5 times, or 5 past a multiple of 6? Or another way to think of it, it's 1 less than a multiple of 6. So like your 5s, your 11s, your 17s, all those. So what do you get for that? So at 5, if our first term is 5 past a multiple of 6, then it's 1, 2, 3, 4, 5, 5. So it's going to be, we're still going to have this term out in front. And we're going to have a negative pi, or a negative square root of 3 over 2. But then what is our other one going to be? Our other one is going to be 10 past a multiple of 6. Or the 10 past the start of a period. So 10 past the start of a period is the same as 4 past the start of a period. So 1, 2, 3, 4. That's going to also be a square root of 3 over 2. So add these together. You get a negative 2 square root of 3 over n pi. A whole lot of work for a lot of zeros, but this is a very interesting situation. There's not really another good way to do it besides just listing out all the cases. So that means we can finally use this formula up here that's been up here since the beginning of the of our time together today. So let's start it. Remember our a of 0, as we determined here, is 0. Our average over the interval is 0. So I'm just not even going to write it down. And all of our b's are 0, remember, because of this here that we said, because f of x is an even function. Okay, so that just leaves us with all of our cosine terms. So notice that all of these have a 2 square root of 3 over pi. So just to make this easier, I'm going to write that out in front. Since it's going to be multiplying everything, we don't need to write it for every single term. Okay. So, when n is a multiple of 6 plus 1, it's going to have this coefficient in front of this term. So, since we took care of the 3 pi, so 3 square root of 2 square root of 3 over pi, all we have left is the 1 over n. But for n equals 1, then it's just going to be 1 over 1. So we don't even care about that. So cosine of, and remember, this L is 1 over 220. So when we take 1 over L, we actually multiply by 220. Pi x. We are finally getting somewhere. Okay, so 2 plus a multiple of 2 plus a multiple of 6. So we don't have any 2 term. We don't have a 3 term. We don't have a 4 term, but we do have a 5 term. Remember, there's a minus sign in front of here. This minus sign is very important. This is going to be minus. Remember that most of that is taken care of, but the 1 over 5 is not taken care of by this out in front, because that's different for each term. That being said, we will continue writing this down. You could multiply these things together, but I prefer to keep them separate. It reminds me what term I'm dealing with. We don't have a multiple of 6 term, but we do have a 1 plus a multiple of 6 term. So this is 1 over 7 cosine 220 pi times 7x. So our next term, what is our next term going to be? This is our 7. We don't have an 8, we don't have a 9, we don't have a 10, but we do have an 11. So I'm going to start writing this over here. 1 over 11 cosine of 220 pi times 11x. We could keep on going further and further on, but I think this is probably good. I think you get the idea of how this thing works. What would our next term be? If this is our 11 term, then our next term would be 13. Our next term after that would be so 13, 14, 15, 16, 17, and then 19, etc., etc., etc. Actually, yeah, it'll be up. It would be yeah, 19 is a term. Um, so yeah, so the harmonics of this are all the 1 plus a multiple of 6 and the 1 minus a multiple. No. As multiple of 6 plus 1, or a multiple of 6 minus 1, or a multiple of 6 plus 5. The relative intensities, so the relative intensities is just a square of the coefficient. And for that, you do have to take this term out in front. Or whatever makes your first term 1. So for our harmonics, our fundamental first harmonic, second, third. So we'll go just as far up as we did the expansion. So the relative intensity of this one is 1. It's our fundamental tone. These don't have anything to do with this. And then we have 1 over 25, and then a 0, and then a 1 over 49, and then 3 more zeros, and then a 1 over 121, and then this continues. So, if you would like to see a good representation of this, I will show you guys one. Okay, so you guys can see this. The red is our original 1 period of our function. And this formula here is what I have to do to get this working right. So it works correctly. It doesn't look the best, but it's correct. The only problem is that it adds 2 terms at a time, because this repeats every 6. So, So this adds 2 terms at a time. There's not really a good way to do it otherwise. So this is the first 2 terms, and then you can keep on adding terms. Yeah. So as you keep on adding terms, it gets closer and closer. This overshoot at the beginning never really goes away. But yeah, you can see that it does get a better and better approximation the more terms you add. I do have one other way to represent this, and I will show that to you guys. Hopefully you guys will be able to hear it, because this is a sound wave representation of it. Okay. Let's turn that up. Okay. So those are the first terms of this series, all played separately at their correct amplitudes. So this is the fundamental tone, and then we got up to the 19 term. So remember, we have 1, 5, 7, and then on from there. This audio file gets up to the 19th term, not 19th term, but the cosine of 19 times all that stuff on the inside. So this will play through once more, all of the tones individually, and then it will add them all up. And you can actually see, unfortunately, this wave gives you a good idea of the sizes and such, but when it starts adding them together, it does not look like our original function. That's because these are all sine waves instead of cosine waves. So it sounds the same, basically, but all the phases are slightly different. Actually, I think it sounds the same as it would normally. Um, there's not really a good way to have a program generate cosine waves. They all generate sine waves because nobody usually cares about this. But here you go. I will play this again for you, and you can listen. I hope this was helpful for understanding Fourier series and how it applies to sound waves. Thank you very much for watching.